Good day, ECO235 students. We continue week 2 with an introduction into topic 2. This topic deals exclusively with nonlinear mathematical economics problems. The following topics will be dealt with in topic 2. We will begin this week with rapid revision of your various rules of differentiation. You will also be introduced to the product rule, quotient rule, and chain rule. This is the content to be covered this week. Then you will continue with partial differentiation and constraint optimization. Constraint optimization that deals with both consumption equilibrium and production equilibrium. You will look at partial elasticities and returns to scale. You will also learn about the Lagrangian multiplier and how it can be used to solve consumption and production problems. So take note that topic 2 will most likely continue till the end of term 3 before we move on to topics 3 and 4 in term 4. The prescribed readings for this section, topic 2, is chapter 5 and chapter 8 of your prescribed textbook. We will begin with revision of the gradient of a linear curve versus a non-linear curve. In economics, many functions you come across may be either linear or non-linear. Linear functions, for instance, are your budget lines and your isocost curves. Your nonlinear functions that you may come across include indifference curves, which you've learnt about in ECO231, and isoquants, for instance. In the first part of this figure, we have a linear function, right? We can see this function is linear. It is a straight line. The degree of this function is 1. That is, the highest exponent is 1. It is expressed as y is a function of x, or y is equal to mx plus c. That is the standard form. M, in this case, which is equal to 2, represents your slope or the gradient of this function. And 4 represents your vertical intercept or the constant of this function. So by seeing that the gradient is 2, we can see that it is constant all along this line. For all points along this line, the gradient is always equal to 2. In the next part of the figure in the slide, we see a nonlinear function. Here, this function has a degree of 2, as can be seen by the variable with the highest exponent. It is equal to 2. Thus, we know that this function will have one turning point. So it is a quadratic function. With a nonlinear function, the gradient or the slope differs at different points along the line. So in order to determine the gradient of a nonlinear function, what do we have to do? Here we have various tangents, and we know that a tangent is a line that touches a curve at one point. The slope of a non-linear function is not constant. We are able to see that. So for a non-linear function, the slope isn't the same at different values of x. So in this figure, we could see the gradient or the slope was constant equal to 2 at all points along the line. However, for a non-linear function, the slope isn't the same at different values of x. So as stated, the slope of this nonlinear function is not constant. Thus, the slope at a given point is measured by the slope of a line drawn tangent to the function at that point. So you saw in the previous figure, there were 3 different tangent lines drawn at different points. And that is why I pointed out that a tangent is a line that is drawn at one point. So the slope at a given point is going to be measured by the slope of that tangent line to the function at that point. So hence, if you want to measure the slope, we're going to need different or separate tangent lines at different points. The slope of the graph of a function is called the derivative of a function. Now, a derivative is the gradient of the tangent to a curve at a point. If you have a function, y is a function of x, as we have here, differentiation is required. Now, differentiation is the process of determining the first derivative of a function, and this is the notation that we will use. F dash of x or f prime x. Another form of notation is saying dy by dx. Note this is not divided by. In Greek symbols, delta would be given by the triangle, and in our language, d represents delta. So this means change in y by change in x. So hence it's dy by dx, not dy divided by dx. So to find out the first derivative of a function, f dash of x, so you first would have to follow the process of differentiation and get the first derivative of the function, and then substitute the x value into this first derivative equation, and then the instantaneous slope at that particular x value would be found. So we'll do a few examples. Before we get to that, there are just a few rules that you would have learnt in ECO 151 that we are going to quickly recap. The constant function rule states that the derivative of a constant function is 0. So if you have a function y is a function of x and it is equal to k, and k is some constant, then the first derivative of that function, f dash of x, is equal to 0. So remember, the constant function rule states that the derivative of a constant function is 0. So let's look at the next example. Here you have y is a function of x and it's equal to 8. Thus, f dash of x is going to be equal to 0 because 8 is a constant. What does this mean? Well, the slope is 0 at all x values. So if you were to plot this graphically, you would just have a horizontal line that cuts the vertical axis at a vertical intercept of 8, and hence the slope is 0 at all x values. Here's one more example. Y is a function of x and it's equal to minus 10. That is just a constant, hence f dash of x is going to be equal to 0. The next rule is the linear function rule. Now, the linear function rule states that the derivative of a linear function is equal to the coefficient of x. So here we have a linear function, y is equal to mx plus c, and the coefficient of x is typically the number that is next to the variable x. M is the coefficient, and we know that to be the gradient of this function. C just represents a constant. And from the previous rule, you know that if you differentiate a constant, it differentiates to 0. Hence, according to the linear function rule, it states that the derivative of the linear function is going to be equal to the coefficient of x, and the coefficient of x here was m. So let's look at an example. Y is a function of x and it's equal to 3x plus 10. Thus, f dash of x is equal to 3. 3, you can see, is the coefficient of x. Thus, the slope is equal to 3 at all x values. And again, if you were to graphically illustrate y is equal to 3x plus 10, you would have an intercept of 10 and your slope would be equal to 3 for all x values. Here's another example. Y is a function of x and it's equal to minus 5x plus 10. Here, f dash of x, or your derivative of that function, is equal to minus 5, which is the coefficient of the variable x. So far, the first two rules are fairly straightforward. The next rule will help you understand even further how we arrived at these answers. The power function rule. Now, the power function rule states that the derivative of a power function, f of x, is equal to kx to the power n. It is going to be equal to the coefficient k times the exponent n that we brought down, multiplied by the variable x, that is then raised to the power n minus 1. So please, you should remember this from ECO 151, the power function rule. So we have our coefficient k times the exponent n multiplied by the variable x raised to the power of n, which is your exponent, minus 1. So for this example, we have f of x is equal to 6x raised to the power of 3. Thus, f dash of x is going to be equal to 6, that's your coefficient, multiplied by 3, that was the power n that was brought down, times the variable x raised to the power of n, which is in this case is 3 minus 1. So 6 times 3 is 18. X to the power of 3 minus 1 is equal to 2. So thus, we can check the instantaneous slope at a particular x value. So when x is equal to 1, the slope is going to be equal to 18, and you substitute the value of x into the first order derivative. And of course, 1 squared is just 1, so 18 times 1 is 18. When x is equal to 2, the slope is going to be equal to 18, and we substitute the 2 into our first order derivative, and that is squared raised to the power of 2. 2 squared is 4, 4 times 18 is 72. Here's one more example that you can work through on your own. Be careful when you have to work with negative numbers and negative powers. Hence, I asked you to revise your work on exponents. The next two rules are fairly straightforward. That is your sum and your difference rule. Now, the sum rule states that you should differentiate each function separately and then add them. So here we have y as a function of x, and it's given by the sum of two functions, g of x plus h of x. So the sum rule says that in order to find the first derivative, you need to get the derivative of these two functions separately and then add. So differentiate them separately and then add. And for this example, we have f of x is equal to x squared plus 5x plus 6. So in order to get the first order derivative of this function, we'll differentiate each and then add. So this would now become 2x, because you bring the power down, multiplied by the coefficient in front of the variable x, which is 1. So that is 2x. And now remember, we have to say 2 minus 1. 2 minus 1 is just 1. So we don't have to write that exponent. And of course, if we differentiate 5x, the power that is at the top of this x here is 1. So it would be 1 times 5 is 5. Now x is raised to the power of 1 minus 1, and x to the power of 0 is just 1. So this just becomes 5. And here's another example. Here we have 3x cubed plus x squared plus 5x plus 6. Hence the first order derivative is going to be 3 times 3 is 9. X raised to the power of 3 minus 1 would give you 2. Here we have 2x, because we bring the 2 down, multiplied by the coefficient, which is 1, times x, and that becomes 2 minus 1. So it's just 2x. And this is simply going to be 5, because we have an exponent of 1 multiplied by 5 times x raised to the power of 1 minus 1, which is 0, and x to the power of 0 is just 1. So that's 5. And you know that if you differentiate a constant, it differentiates to 0. So that is your sum rule. Similarly, your difference rule applies the same logic. I will have to end this recording at this point, and we will continue with the difference rule in part 2.